Welcome once again to the class and welcome once again to the channel, and let's move on towards our next topic of discussion of today, which is magnetic moment of nuclei. We are going to discuss this particular concept, magnetic moment of nuclei. Okay, and what are Schmidt's lines? Okay, the many a times a question is asked about the Schmidt lines. Okay, so SCHMIDT. Okay, Schmidt lines. So I am going to discuss these Schmidt lines also in the end of the video, but we will start from the magnetic moment of the nuclei, because only if we understand the magnetic moment of nuclei, only then can we understand what are Schmidt lines. Okay, so the pronunciation is Schmidt. Okay, Schmidt lines. So let us understand. So even number of nucleons of any kind always gives the resultant spin I equal to 0. We have already learnt, right, that if there are even number of nucleons, that is number of protons is also even and number of neutrons is also even, then what happens? Then the resultant spin I is equal to 0 in that case. The resultant spin I is equal to 0 in that case. Okay, so and why is the resultant spin I equal to 0 in that case? Because when there are even number of protons or even number of neutrons, then when you write the nuclear configuration, the nucleons get paired up. Okay, while writing the nuclear configuration, the while writing the nuclear configuration, the nucleons get paired up. Okay, in case of even number of nucleons. So as the nucleons get paired up, what happens? It gives you resultant spin equal to 0. Okay, and parity is even. We have already learnt, right? In such cases the parity is even or plus 1 or positive. That is, parity is even, plus 1 or positive, and on the other hand the resultant spin is equal to 0. Okay, resultant spin I is equal to 0. Hence the magnetic moment of even nucleus, okay, as the resultant spin is 0, so it has been found experimentally that the magnetic moment of such a nuclei, which has even number of protons and even number of neutrons, okay, number of proton is also even, number of neutron is also even, and obviously the atomic mass number A, which is equal to total number of protons plus total number of neutrons. What is atomic mass number A? Atomic mass number A is equal to total number of protons plus total number of neutrons. Yeah, right. So A equal to Z plus N, capital A equal to capital Z plus capital N, and capital Z is also even and capital N is also even, so capital A will also be even, right? So the magnetic moment of even nucleus is what? It is equal to 0. It is experimentally determined. Fact. So magnetic moment of even nucleus is 0. So mu I, what does it mean by mu I? Mu I means magnetic moment. Okay, mu I means magnetic moment of a particular nucleus. So we represent the magnetic moment of any particular nucleus by the symbol mu I. Okay, mu I is the symbol which represents magnetic moment of any nucleus. Okay, now mu I EE. Okay, it is EE written over here. What is written over here? EE has been written over here. Okay, EE has been written over here. Now what does it mean by EE? EE means even. Okay, so mu I, that is magnetic moment for even nucleus. EE means even. That is equal to your 0. This is what? This is an experimentally determined fact. Okay, this is an experimentally determined fact. Now, in an odd A nucleus, what happens when the atomic mass number A is odd? This was the case when A was even. Okay, this was the case when atomic mass number A was your even. Okay, what was the first case? This was your even, okay, this was even this was even, and even this was even. This was your first case. So as everything was even, so mu I was equal to 0 in such a case. In such a case, mu I was equal to your 0. Okay, clearly A is also even, Z is also even, and N is also even. So that's why mu I equal to 0 in this case. Now in an odd A nucleus, it is last odd nucleon, that is in odd A nucleus, what is the possibility? If we are discussing this particular case now, which case are we discussing? We are discussing this particular case right now. Okay, so let us discuss this particular case. So what does it say? Let me take the next page. So we have atomic mass number A equal to odd. Okay, now you know this very well that A is equal to what? It is equal to Z plus N. Okay, now this is what? This is number of protons. This is what? This is number of neutrons. And this is what? Total number of nucleons. Okay, this is total number of nucleons. Now this is suppose your odd. This is suppose your odd. Then what will happen? Then two cases are possible. This is even, then this must be odd. Okay, and this is again odd. So two cases are possible, right? Then either this must be odd, then this will be even, because even plus odd is the thing which gives you odd, right? Even plus odd is the thing which gives you odd. If you add two odd numbers, then what will happen? Suppose if number of proton is also odd and number of neutron is also odd, suppose, then what will happen? If P and N both are odd, then obviously A will be even, because odd plus odd is even. So then A becomes even in that case. Okay, that case we are not going to discuss. That case we are not going to discuss. So clearly A equal to odd has two possible cases. Either it can be even odd nucleus. Okay, for A equal to odd, either it can be even odd nucleus. Okay, either it can be even odd, either it can be even odd nucleus, or it can be either odd even nucleus. Okay, so either it can be even odd nucleus or it can be odd even nucleus. Both the cases are possible. So that's what has been discussed over here. Let us see. In an odd A nucleus, it is the last odd nucleon, that is last odd nucleon means suppose if protons are even in number, so proton will not affect the magnetic moment. Okay, if proton is even number, then proton will not affect the magnetic moment. If neutron is even number, then neutron will not affect the magnetic moment. Okay, so whatever entity is odd, in this case number of neutron is odd, in this case number of proton is odd. Okay, so only the odd entities will affect the magnetic moment, right? So over here number of protons is what? It is odd. Not number of proton, number of neutron is odd in this case, and in this case number of proton is odd. Okay, so in this case, as the number of proton is odd, so this proton will determine the magnetic moment, and in this case the number of neutron is odd, so neutron will decide the magnetic moment, and that too odd neutron. Okay, in this case what will decide magnetic moment? The odd neutron. The odd neutron will decide the magnetic moment, and in this case what will decide the magnetic moment? The odd proton. Okay, because suppose the odd number is suppose 13, the odd number is suppose 13, then what will happen? The 12 nucleons will be paired up, and one nucleon will be unpaired. What will happen? 13 is equal to 12 plus 1. So the 12 nucleons will be paired up, and one will be odd man out. One will remain, which will be unpaired. Okay, so the unpaired neutron will decide in this case in even odd, and in odd even unpaired proton will decide. Okay, in this case unpaired neutron will decide, in this case unpaired proton will decide. Okay, so this is the thing. So in an odd A nucleus, it is last odd nucleon, neutron or proton, which determines the magnetic moment, right? It is last odd nucleon which determines the magnetic moment. For such a nucleus, I equal to J. Okay. Now, for such a nucleus, capital I, what does it mean by capital I? Capital I means your spin. Okay. Capital I is your resultant spin. Now resultant spin is equal to J of the unpaired nucleon. Okay, resultant spin is equal to J of unpaired nucleon. We have already seen this in the previous lectures, right? We have already seen this in the previous lectures. So the resultant spin I is equal to your J of the unpaired nucleon. What does it mean by J? J means when you write the nuclear configuration, and suppose the last nucleon goes in a certain subshell, the last unpaired nucleon goes in a certain subshell, then whatever will be the value of J, whatever will be the value of J for that particular subshell in which the last nucleon resides. Okay, whatever will be the value of J for that subshell in which the unpaired nucleon resides, that will be the value of intrinsic spin for that intrinsic ground state spin for that nucleus. Okay, so that is the case. For such a nucleus I equal to J, where J is the total angular momentum of the last unpaired nucleon. Okay, where J is what? Total angular momentum, that is your J quantum number. Okay, of the last, which is written as suffix. Okay, you write it like this, right? 6h 9 by 2. Okay, you write it like this, right? So all these things, this 9 by 2 is the value of J in that. Okay, this 9 by 2 is what? The value of J. So for such a nucleus I equal to J, where J is the total angular momentum of the last unpaired nucleon. Okay, what is the J? What is J over here? J is the total angular momentum of the last unpaired nucleon. J is total angular momentum of last unpaired nucleon. So that is the thing. J is total angular momentum of last unpaired nucleon. Now, orbital nuclear angular momentum and intrinsic nuclear spin angular momentum. Okay, now this is spin orbit coupling about which we have already learnt. We have already learnt about spin orbit coupling in the preceding classes, right? So orbital nuclear angular momentum and intrinsic nuclear spin angular momentum of the unpaired nucleon, okay, couple to constitute total angular momentum J. Now total angular momentum J equal to L plus minus S. What does it mean by total angular momentum J? Total angular momentum J is equal to L plus minus S. Okay, this also we have already learned. Now what is L? L is orbital nuclear angular momentum. L is what? Orbital nuclear angular momentum. And S is what? Intrinsic nuclear spin angular momentum. S is what? Intrinsic nuclear spin angular momentum. Okay, and J is what? Total angular momentum. So total angular momentum is equal to orbital nuclear angular momentum and intrinsic spin nuclear angular momentum. Their sum together gives total angular momentum. Okay, so L is orbital and nuclear angular momentum and S is intrinsic nuclear spin angular momentum. And when you add L and S together, whenever coupling of L and S takes place, it gives you the value of J, that is total angular momentum J. Now S has two possible values, plus half and minus half. As S has two possible values, plus half and minus half, so it will be equal to J equal to L plus minus half. J will have a value equal to L plus minus half. Okay. Now total magnetic moment of nuclei. What is total magnetic moment of nuclei? Let us see. Now total magnetic moment of nuclei will be equal to what? Similarly, as J equal to L plus S, so the total magnetic moment of nuclei will be a vector sum of mu J equal to mu L vector plus mu S vector. Mu J vector will be equal to mu L vector plus mu S vector. Please listen to it carefully. Okay, mu J vector is equal to mu L vector plus mu S vector. Now what is this mu J vector? What does it mean by mu J vector? Mu J vector is the magnetic moment due to total angular momentum. Okay, so let us write it down on the next page. Let us write it down properly on the next page. So mu J vector is equal to, okay, what does it mean? It is magnetic moment on account of total angular momentum J of nucleus. Okay, this is mu J, magnetic moment on account of total angular momentum J of nucleus. Now what does it mean by mu L? Okay, it is orbital, okay, magnetic moment, let us say it is also magnetic moment on account of orbital angular momentum L of nucleus, right? This is the definition of mu L. Okay, and what is mu S? Mu S is magnetic moment on account of spin angular momentum S of okay, so mu S is what? Magnetic moment on account of spin angular momentum S of nucleus. Okay, so mu S is magnetic moment on account of spin angular momentum S of the nucleus. Okay, so this is the thing. Now mu J is, as J equal to L plus S, so mu J vector will be equal to mu L vector plus mu S vector. Okay, so this is the thing. Now mu J vector will be equal to, now you know this very well, you have already learned in atomic and molecular physics, and if you haven't learned the atomic and molecular physics, still I would like to tell this particular fact to you, just to remember for the time being. Okay, just remember this particular fact for the time being. Okay, this is the value of mu L. Okay, what does it mean by mu n? Mu n is Bohr magneton. Mu n is Bohr magneton. Okay, mu L is Bohr magneton. And how is mu s defined? Again, in terms of Bohr magneton, not Bohr magneton, nuclear magneton. Sorry, not Bohr magneton, nuclear magneton. Okay, so it is defined something like this. Okay, so this is the definition of mu L in units of nuclear magneton. So mu L vector equal to GL L vector divided by h cut nuclear magneton, and mu s vector is GS into s vector divided by h cut nuclear magneton. Okay, so these two formulas also you should keep in mind. These two formulas also you should keep in mind. Now when you substitute these two values in this particular expression, then you can take out mu n by h cut common. You can take out mu n by h cut common from here. So as soon as you take those things common from here, the expression looks something like this. As soon as you take this particular factor common from here, the expression looks something like this. Now GL L vector plus GS S vector, what does it mean by G? What does it mean by G? G means Landis splitting factor. Okay, what does it mean by G? G means Landis splitting factor. Okay, what does it mean by G? G means Landis splitting factor. Okay, G means Landis splitting factor. Now GL will be Landis splitting factor for orbital angular momentum. Okay, GL will be Landis splitting factor for orbital angular momentum of nucleus, and GS will be what? GS will be your Landis splitting factor for spin angular momentum. GS will be Landis splitting factor for spin angular momentum. Okay, so this is the thing. Now for proton and neutron, the value of GL and GS, the value of GL and GS for proton and neutron will be different, right? The value of GL and GS for proton and neutron will be different. So for proton, GL is equal to 1. Okay, so this particular value is equal to 1 for proton, and for neutron GL is equal to 0. This value of GL is equal to 0 for neutron. So for neutron GL 0, proton GL equal to 1. For proton GS equal to GP, it is equal to 5.58 for proton. These values you must remember. Okay, and for neutron GS equal to GN. GN means for neutron, N for neutron. GS equal to GP over here means GP means P for proton. Okay, so GS equal to GP equal to 5.58 for proton, GS equal to GN equal to minus 3.82 for neutron, GL equal to 0 for neutron, GL equal to 1 for proton. Okay, so as soon as you substitute all these values, what happens? These are the values which we have already discussed. Okay, so we will substitute it in the very end. We will substitute all these values in the very end. Okay, so how to find the magnitude of mu j along j direction? Okay, from here onwards we will discuss in the next class. Okay, from here onwards up to here, the total magnetic moment of the nuclei we have already learnt. Okay, what is total magnetic moment of nuclei? We have already learnt it. Okay, but the main Schmidt lines and etc., all those things from there onwards we will learn in the next class. So from here onwards, from here onwards. Okay, just mark this page. From here onwards we will learn in the next class. Okay, so thank you very much. Please like the video, please subscribe to our channel, because all these videos take a lot of effort. Okay, all these videos need a lot of effort, so please like the videos, please subscribe the channel. Okay, Thank you very much. Jai Hind, Jai Bharat.